Hello engineers. Okay, last class we discussed about the common source amplifier with a resistive load. So there was that you have a resistance and with that you have a MOSFET and I represent it in such a way that okay, you have an input at the gate and this source terminal is grounded and that here is a drain resistance that is RD, this is VDD and here you have output. You are talking about the output at the drain and you are giving the input at the gate and the common is both for that is source. That is a common source amplifier with a resistive load. So in that we discussed that the output can vary, that V out can vary from VDD to what? That the maximum voltage of the output will be VDD when the current is 0 and it is maintain saturation till that is the VD side, that is the voltage here, that is VDS, and the VDS is what? That is the minimum voltage when the V out is maintained that saturation region. So I represent in such a way okay, you have a, in last class we discussed that you have a ID versus VGS graph and your output, that current is looking like this. Similarly, your output voltage, let the output voltage here, I am representing that V out with respect of VGS. When the current is 0, this is VDD and VDD is decreasing and then it will be like this, that is called VD side, that is VGS minus VTS, the overdrive voltage of the MOSFET. After that the MOSFET is entering a linear region. So if you talk about that is cut off and that is the region where it is maintained in saturation and after that it will be a linear. So output can be vary from VDD to that is maintained that this voltage is VDD to VD side. So your output can be vary, that headroom of the MOSFET for this type of circuit, that is resistive load, it can be vary from VDD to near about VDD to VD side, that is VGS minus VTS. Okay. And you find that what will be the operating voltage, let this the operating voltage X and you are tweaking that X with a delta X and you find that the large amount of change at the output. Of course, it will be a invert like this. Okay. So this was happened by the resistive load. Now we know that resistance is a problem when we are talking about the fabrication. You require a poly resistance, so it will take a area. And we know that VLSI is a monolithography. We will talk in such a way that everything we can design with the MOSFET only. So can we convert this RD with the MOSFET? So we are converting that, we are assuming the load is diode based load. So now I am going for common source stage, yeah, common source amplifier with diode connected. So in the place of resistance, I am replacing the resistance and use a diode based connection. Just then think in such a way, okay, you have a circuit that you have a common source amplifier where that you have an input here, you are talking about the output here and the source is common, that is make it ground here, and now I am using a load as a diode connected. Well, let I am using a MOSFET and I am just connecting like this. So what is this? Just firstly understand this part. So whenever you have a MOSFET like NMOS, you can connect the drain with gate. If you are connected drain with gate, that 3-terminal device become a 2-terminal device and it is act like a diode. And similarly, if you have a PMOS, let this is PMOS, that you are connected like this. Okay, that is PMOS based diode, this is NMOS based diode. Just simply you are connecting that drain with a gate. And what is happening if you are connecting drain and gate? So what will happen, that you know that VDS is greater than equal to VGS minus VTS for MOSFET in saturation region. And if that drain greater than equal to VG minus VTH, and if drain voltage and gate voltage is same, so always this voltage will be greater than VD minus VTH because VG is VD. So that the MOSFET is always in saturation. Always in saturation. When the MOSFET is on, that is always it is in saturation. What is the meaning of on? That means let this is VDD and here you have a source that is Vx, that is VDD minus Vx greater than equal to VTH for the MOSFET on. VGS greater than VTH. So that VDD minus VTH is greater than equal to, or I can say that this is Vx is less than VDD minus VTH. So if this voltage is VDD minus VTH, then MOSFET is on. And after that it will be not on. It is not behave like a on. So the output can be moved to maximum value is VDD minus VTH there. In the last class that was 0. Here that is VDD minus VTH. And similarly the minimum voltage to make that MOSFET in saturation, that is VD sat. So we can think in such a way, if you are using a diode based connected load in place of resistant, the swing is reduces. In a previous case that the swing was near to VDD to VD sat, and here that the Vx is VDD minus VTH, that will be the maximum voltage it can attain to make that MOSFET is on. If it is less than that, MOSFET is on and it is maintained in saturation region. Vx never be more than VDD minus VTH. So it is lying between VDD minus VTH to VD sat. Okay. So let's talk about that diode base connected. So this is NMOS and I am connecting in such a way. So if I am going for a small signal model of that MOSFET, so I am using that, I am putting that is V here and I'm finding the I. So what is that impedance of that? Because we are always talking about that, firstly we set the operating point and then we talk about the small signal model and then we can find the gain. So as we know that with the resistance, that gain is minus GM RD parallel of R0. Now load is diode based connected. So when we are trying to find out what is the output impedance of that, what is the impedance of that diode base connected, let's try it. I am just using voltage here and find that the I here. So what is the small signal model of that? We know that the small signal model is like this. Okay, let lambda is not 0. If lambda is 0, then make that R0 is infinite, it is open circuit. But that I am just thinking that lambda is not 0, that here is the effect of channel length modulation. So this is what, that is your gate voltage And for a small signal model, this VDD is become a short with a ground. So this is grounded here. And gate and drain are connected. So you can say that it is connected like this. Okay. And here it is GM VGS. And I am saying that okay, this is also grounded. And you are talking about here you have a V and you are talking about this is I. So this node has V here. So what is I? Basically VGS is what? That is gate voltage is 0 and source voltage is V. So this is GMV on the upside, or you can say the minus GMV on the downside. So that circuit like that, this is the way like this you can represent in such a way. This is minus GMV R naught with that voltage V here, and this is R naught, and you are talking about what is the I here, and this is also grounded. So what is I? I is basically that you are using at KCL here, that I is entering, GMV is upward, minus GMV is downward, so upward is GMV, and this is V minus 0 upon R naught. So I can say that this is GMV plus V upon R naught. So what is V upon I? That V upon I will be 1 by GM parallel of R naught. 1 by GM parallel of R naught. If it is R naught, this is M1, so put it R naught 1. If it is M2, you can put it R naught 2. So as you know that if you are using a diode based load, so in a previous that resistive load that was RD, and it is fixed for DC, for AC, for everywhere. For a small signal model that was RD also. And once you talk about that a small signal model of the diode based connected load, so that this small signal model like this, and that load is 1 by GM parallel of R naught. You can replace with 1 by GM parallel of R naught. So you have a diode connected load with the like this, and you are providing the input here, and you are talking about the output at this node, and this is VDD. So the small signal model is like this, that is it is grounded, this is resistance, that is 1 by GM, let this is M1 and this is M2, so this is 1 by GM2 parallel of R naught 2, and this is connected in such a way like this, and this is also delta X, and you are talking. Okay. And if 1 by GM2 is small as compared to R2, so you can say that this is what? That is V out by V in is what? Just like a basic case, that is minus GM R naught parallel of RD. This is M1, so R naught 1 parallel of RD. So this is minus GM1 R naught 1 parallel of this, that is 1 by GM2 parallel of R naught 2 parallel of R naught 1. This is the gain with a resistive load, and let 1 by GM2 is near small to R1, R naught 1 and R naught 2, so it is nearly about minus GM1 upon GM2. This is the gain. So V out by V in is minus GM1 upon GM2. In the previous case that was minus GM1 R naught parallel of RD. Now that gain is minus GM1 upon GM2, because that is 1 upon GM2 parallel of R naught, I can say that approximately 1 by GM2. Okay. So if you are changes the load in place of RD. If you are using a MOSFET based load, that is a diode based load, so of course the gain will changes. That gain is changes with a minus GM1 upon GM2. And if you are putting that, okay, what is the gain here? That is AV is equal to minus GM1 upon GM2, and this is also called, you can say that simply that under root 2 mu n CUXW by L 1 into ID. This is 2 mu n, because this is M1 is a MOSFET as a N type, that mu n COX W by L of 1, due to M1 it is 1, ID 1, and this is 2 mu n COX W by L of 2 into ID. Yes, hello. This is the way you can understand. Okay, the gain is changes. Okay, and you can make it, let both MOSFET have a same current, both have a same mobility, same oxide, so that current will be dependent on W by L of 1 and W by L of 2, that is AV is equal to F everything, because they are in series, and ID1 is equal to ID2, so you can say that this is W by L of 1 upon W by L of 2. It dependent on the width of the MOSFET, width and length. W by L of 1 upon W by L of 2. So this is the way you can analyze, okay, that if you are using that as a diode connected base circuit, so now that gain is dependent on the parameter of the MOSFET, W by L of 1 and W by L of 2. So what is the advantage of that? You can think in such a way, okay, if you are using this or you are using with a resistance, so that gain is dependent on, if you are using a resistance with common source amplifier like this, so what is the advantage? You can think that what is the gain here? That is minus GM RD parallel of R naught, and GM is a parameter of mobility and oxide and capacitance. So everything, that gain is minus GM RD parallel of R naught. There is a difference, that the parameter, that if this mobility is effect, if the temperature is effect, if anything is affected, that will be the gain will affect. Okay, but the swing is from VDD to VD sat. But the swing is what? That swing is providing VDD to VDD sat. That the output can be shifted from VDD to VD sat with the resistive load. So that good part is that the higher is swing. But the bad part is that first one is RD fabrication, that resistance fabrication will be tough in a VLSI, because here will be required a polysilica resistance. Okay, you are using a polysilica polyresistors. Okay, and similarly if you are using this with that resistive load, you will find that GM factor and GM will be affected with the temperature, with the mobility, with everything. It is affected. That is process supply variation, PVT, that is process supply voltage and temperature, that is a process variation. Mobility, threshold will be affected. Okay, and if we are using this MOSFET with a diode based load, let I am using the input here and this is the output, and let this is M2 and this is M1. So now what is the gain? That is minus GM1 upon GM2, nearly about like this. So if you have a parameter variation, a process variation, so everyone have that both MOSFET have a process variation, that will be nullified, and this is nearly about what? That is minus of under root W by L of 1 upon W by L of 2 there. Is it? So the good part is there is no any process variation effect, that is don't that much of effect of process variation. But the problem is here that what is Vout? Vout is not reaches to VDD. it will be reaches to VDD minus VTH to VD side. So the swing is not to VDD, it is swinging to VDD minus VD side, VDD minus VTH to VD side. So if you are using a diode connected base circuit, if that dimension is same, it is act like a buffer. Why it is be buffered here? How it will be look like a buffer? No, it's not be like a buffer, it will behave like an inverter here. If you are providing the input is 0, that V out is what? That is current is 0, that VDD. Similarly here, if you are providing the input is 0, so that this MOSFET is not on, that there is no current, that V out is what reaches to? It is VDD minus VTH, the maximum voltage. If input is high, then it will be towards the ground. So it is behave like a, not a buffer, it is act like an inverter here. Common source amplifier act like an inverter. Okay. Okay. That is low swing for, of course, that not a low swing, I can say that is comparatively to this, it is less swing. It is a small swing in compared to that resistive load. This is VDD to VD side, and it is not VDD, it is nearly about VDD. That is 1, so it will be 0.9, because as per that current will be going on, that have an effect. Because once that input is reaches to VTH, then the MOSFET is on. It is nearly about VDD minus ID RD, and the current at the VTH, it is nearly about microampere. Okay. So it is very small, but that V out is VDD minus ID, ID is nearly to microampere. That is, it is just at VTH, and at VTH it will be reaches to saturation region, because the drain voltage is very high, and when that V out is V out is decreasing from VDD minus ID as per the current is increases, MOSFET enter in a linear region. So if I am talking about the region for that, what is the swing of the V out for making that is MOSFET in saturation region? The swing is nearly about VDD to VD side. But if you are talking about the diode base connected, this is perfectly VDD minus VTH, then only this MOSFET is on. It is always in saturation, but just the condition is must be on. So if it is greater than VDD minus VTH, this M2 will be off, because this condition is VGS greater than VTH will fail. And we discussed that in a PMOS charging or NMOS charging. So if you are using a pull-up network as an NMOS, that maximum voltage is possible at the source side is VDD minus VTH. For a PMOS, it will be reaches to the drain is VDD. So PMOS is good for charging and NMOS is not good for charging. So it is VDD minus VTH. And that maintain that saturation to VDD minus VTH to VD side. Is it? Yes. Yes, anyone have a question here? Yes. If W by L is same or not, that is always it is like common source amplifier by resistive load, by diode, by any of that. If you are using a current source load, anything, if you are using that CMOS common source amplifier is always behave like an inverter here. There is no meaning that the W by L is same. There is no meaning. Inverter means what? You are proving that input is 0, output is 1. If the input is 1, the output is 0. Just like this. Because inverter is talking about the level. The analog is working in terms of 0 to 1. The transition state, when the input is changing from 0 to 1, the input is changing from 0 to VDD, what will happen? If you are talking about perfectly 0 and perfectly VDD, then only we can talk about the digital, that is for the 0 it is V out is VDD, for VDD it will be that V out is nearly about 0. Is it? So common source amplifier is always behave like an inverter. There is no meaning that W by L is same or something like this. It is behave like that. It will be swing from VDD to 0 for this type of circuit. For that it will be swing from VDD minus VTH to that 0. Is it? Oh, yes, is it okay? So I am just explaining in such a way that if you are using a diode connected base load, so that there is no any process variation effect, because both have a variation is minus gm1 upon gm2, both have a transconductance in a ratio, so that mobility effect or oxide effect, capacitance effect, threshold effect, everything, temperature effect, everything will be nullified, because both MOSFET in the same way, and if any one of that temperature effect, both also have a effect. So that's why I can say that there will be a not too much effect of that of process variation. But the problem is this: if you are using this, that the swing is limited. It's not swing is from VDD to something. Okay, and I am talking the swing in terms of saturation region. I am not talking about the whole region. I am just talking about the saturation region. For the saturation region, this swing is possible. Yes, is it okay? Okay. Uh, so let's talk about what is the load line. Of course, you must have a basic understanding of load line. Uh, this is good or bad. Okay, so if you are talking about this and you have a VDD, okay, so you know that ID versus uh, V out. If V out is changing, so if you are talking about MOSFET, the MOSFET is act like this, that current in such a way, let lambda is 0, so that it will be a straight line. If lambda is not 0, it will be showing some slope. That channel length modulation, let I am assuming the lambda is 0. So R naught is infinite, and will be that current will be, the GDS is 0, R naught is infinite. And due to this you have a resistive load, so it will be showing like this. At VDD it will be 0 current, and the maximum current is VDD by RD, okay, when V out is 0. So this is the way. But when you are using a resistive, if you are using that load as diode connected base, if I am using this as diode connected base load, that is V input is here and here, and this is V out. Now I am using the diode connected load. The common source stays with the diode connected, and let this is NMOS. Okay, you can use as a PMOS also, that use a PMOS and use a gate and drain is sorted. Okay, so now if you are looking this circuit, that the diode, that what will happen, just for a resistance it is looking like this. This is minus of something, slope is negative. But if you are looking at this will be here like this. This will be the slope. This will be the slope what? This will be that waveform. Okay, so if you are talking about the diode connected, that load line is like this. Okay, it is looking like this, dear. So it will be a problem. So that's why it is not providing a good gain. Minus GM1 upon GM2. It will be affect your gain. Okay. So for that reason you must satisfy that MOSFET must in a saturation region. So you can put your lower VGS. At lower VGS you will find it make like this. Okay, that MOSFET is like this and it is maintained. So you are using this. Okay, lower gate voltage. If you are using a lower gate voltage, then only you will find that MOSFET is maintained in saturation region. If you are going for higher Vx, higher gate voltage, maybe that MOSFET may enter in a linear region. This will not provide that particular resistance like load line like this. For 1 by Gm it will be like this there. Is it? So this is 1 by Gm. Now that load will be 1 by Gm. So it will be like this, and that's why it is showing something that it may be for this MOSFET it is saturation for higher voltage, but for that it will be a problem. So you go for lower Vx voltage, lower gate voltage. So the gain is not too much high, that AB is minus Gm1 upon Gm2. And let this is M1 is here and M2 is here. Yes, another question. Sir, why common source amplifier the resistive we called it source degeneration? Source degeneration is a different thing there. Source degeneration is not a common source amplifier. We will use a source degeneration when we are putting a resistance at the source. That is a different part. We discuss a source degeneration. This is a common source amplifier. Common source amplifier with source degeneration, where I am using a RS resistance, and that RS resistance behave like a negative feedback. Okay, as per the gate voltage increases, as per the source voltage will increases, as that the VGS is decreases. So that is source will degenerate to make that gate voltage would be fixed. If you are trying to hear what is happening, you can increase the gate voltage as per you want. You can change that delta V here, because this source voltage is grounded. That VGS is delta V. This is gate voltage. This is equal to gate voltage. So you can increase the gate voltage. There is no any requirement. There is no any feedback. Just like this, you are riding your motorcycle and you don't have a brain. Okay, you can accelerate as much as you want. It may be after that it will be a problem, but you can. But I am using one resistance here that police are present here, or any speed meter is present here, or anything that camera will be present, or anything your brain is actively working. So if you are going for more than 80 km per hour or 100 km per hour, your brain will guide you. There you are going too much fast. It may be a problem. Okay, so that is a negative feedback you have, and you can reduce your accelerator, or you are putting that brake. So source degeneration is just like this. You are increasing that acceleration. The feedback is your VGS. Now here that source is grounded. In a source degeneration you have a resistance, and that will be that source voltage will increase as per VGS is decreases, so that you can down your gate voltage. Okay, it is make that stable. Okay, as per the gain will be increases, you are going towards instability. Okay, you are going for an accident. And if you are using at that is one resistance, that is source resistance, it will be protect your device. So we will discuss source degeneration. I think in a next class we will discuss the source degeneration. But now it is just make that source is grounded. Okay, I am not using any resistance here. Make that source is grounded here. Okay. Yes, is it okay? Sure. Great. Let's talk about common source amplifier. With active load, or not a current source load, or I think. So in last class we discussed that okay, you have a current source load with this, and we discussed about that okay, you have a V input and you have a output, and you have a drain current and you have VDD. If this common source amplifier with a diode connected load, current source load. So if you are talking about the small signal model, the ideal diode is behave like an open circuit. And let this is current, that resistance is R, let this is RD. So what will be the gain? This is minus GM, that is let this resistance of the drain current is RD parallel of R0. And if it is ideal, the RD is very high, so this is minus GM-R0, nearly about minus GM-R0. That is called intrinsic gain. In one line, they can be asked what is the gain here. This is called intrinsic gain. Okay, most of that MTech interview, most of that IIT ask in such a way, if you are going for MTech, they will provide this type of questions and tell that, okay, what is that happening here? They can talk about the input impedance and output impedance also by the cascading that MOSFET on the drain side. We will discuss. We are going slowly on that part, but just collect all these things in your mind, in your copy, and just think, okay, what will happen here? I am just using a diode, that current source, so that this resistance is very, very high, and so that minus GM RD parallel RD is nearly about, I am saying that the RD of that diode, that current source is nearly about infinite. It is very, very high. Ideally, it is infinite, and practically it is very, very large. So this is minus GMRD parallel of R naught, that is minus GMR naught, that is intrinsic gain. This is called intrinsic gain of the MOSFET. That is the maximum gain possible by the MOSFET. Okay, now I am using a current source load with a MOSFET. If I am using this, okay, you have a MOSFET here. Let I am using a PMOS with a V bias. Okay, and now you have a, this is V in here and this is V out. Now I am using one MOSFET as a current load, okay, where that gate voltage is V bias and here it is VDD, and you are talking about this. Okay. So what is happening at here, by this V bias, by the VSG, you can determine as what is that current, what is the channel here, that VDD minus V bias will your VSG. If VDD minus V bias is greater than equal to mod VTH, so V bias is VDD minus VTH, okay, and it is happening here, okay. And if you're talking about what will be that maximum swing will be possible, so you can say that this swing will be what, that will be V out is, this is plus minus mod VD sat. For PMOS it is VDS, and for NMOS it is VDS. For PMOS I am just writing the mod VDS. So just in such a way you can say that what is the maximum peak is possible by this MOSFET if you are using a current source as a load with the PMOS. So it is VDD minus of that VDS, mod VDS. So I can say that VD sat. Okay. And that lower side is what, at lower side it VD sat for a NMOS. Is it? Or you can say that VDD minus mod of VGS2 minus VTH2, if let this is MOSFET M2. So this is VDD minus mod VGS2 minus VTH2 to VGS1 minus VTH1. Okay, because the VD sat is the minimum voltage required to make that drain, is make that MOSFET in saturation region, that is VD sat. And if the minimum voltage required to make that saturation is VD sat, so this voltage VDD minus VD sat will be the maximum voltage is obtained at here. That is VDD minus VD sat to VD sat. That is the swing. Okay. So just think in such a way, okay, if you are using a resistive load and you have an input here, you have a resistance and you have an output. The problem was what, when that if you are fabricated the R in a VLSI in a chip designing, it will be tough. So you are replacing the load with a diode connector or current source load. So this swing was what, that swing is like this. It is from VDD to VD sat. Hello, for saturation region. It is like this. But when I am talking about, okay, you have a load is current load with that MOSFET is a PMOS. This MOSFET is behave like a current source. And now you have a V in here and this is grounded and this is V out and this is VDD there. Just think like that, you just think like a circuit designer. Okay, you are using that load as a current. So now this will be not to VDD, this have a limitation of something that will be VDD minus mod VD set to VD set. Okay, the swing is reduces. But as compared to load of that diode connect, that was VDD minus VTH. And this is VDD minus VD set. It is less as compared to previous one. That this will have a high swing as compared to diode connected base load. This swing is higher. But the maximum swing is possible by the resistive load. But the problem is that resistance fabrication is very tough. So we can replace this resistance. Okay, if you are designing a layout of that, it will take large area because R is 10 kilo ohm or 50 kilo ohm and like this. And this will provide a higher layout. Now if you are using this, you have a 2 MOSFET only. One MOSFET you are providing the gate voltage a V band and another voltage is providing a V in. It is very small as a layout. If you are going for layout design, there is only a one MOSFET and here it is one MOSFET that have a gate voltage is V bias. Here will be, let this is source is here, that will be a VDD. It is connected to VDD. This and this is connected to as like a output, and this have a V input, and this source is grounded. The load is that layout is completed here, and you can use a tap architecture. Of course, the body connection. For a PMOS you are using N tap, for a NMOS you are using P tap, and the latch up problem was solved. But once you are going for this type of layout, it have a resistance with a poly. Okay, that will be a poly. You are just think in a way ki, okay, one poly is here, one poly is here, one poly is here, and you are connected in such a way, and every resistance that poly, let make it 1 kilo ohm, and it is let the 10 kilo ohm, 1 kilo ohm with this to series to this to this to this, like this, positive negative negative positive positive negative, because you are making a series circuit like this now. 1 kilo ohm plus 1 kilo ohm plus 1 kilo ohm plus 1 kilo ohm plus 1 kilo ohm, it become a 10 kilo ohm. You require a 10 poly. Okay, I am not using poly as like a rows. I am using as a column. So in a x direction it can increase. We cannot increase in the y direction. We can increase in such direction, and this positive, this negative will connected to this positive, this negative will connected to this positive. Like this, I am just connecting in such a way, and it become a 10 kilo ohm. It is too bulky there. And when you go for that RC extraction of that, you will find that it is not 10 kilo, it is more than that. That poly have also have a that resistance. Okay, and a capacitance also. It is parasitics also in there. So that's why that analog circuit designer can use resistor, but as a layout designer, if you are thinking about the layout, so layout will always think such a, okay, just replace this resistance there and use a MOSFET. That will be easy for as analog layout. Okay, because as per the resistance will have high at, it will take too much space as an analog circuit, analog layout design, and it will be increases the complexity. So you are increases 10 MOSFET as 10 poly. Let the poly resistance. If I am not using metal resistance. Metal resistance is in terms of 1 ohm. It is very small. It is less than, this is 10 milliohm. So for poly it will providing a higher resistance. So you are using a poly resistance, and you are increases in arrange in such a way that it become a series, and it is become a 10 kilo ohm. You have a lot of area will covered by the resistance only, and you can design a MOSFET in a small that much area. So that is the this is the wastage of area there. So that's why we are always thinking like, okay, use a MOSFET in place of resistor. So I am using a reduce that resistance, that fabrication step. So I am just avoid that. Just like an inductor, inductor is also very tough to fabricate there. So we can replace the resistor and use a MOSFET. That's why VLSI is called monolithography. And in a single chip, you can fabricate everything. By the help of photolithography and photoresist, you are using a positive photoresist or negative photoresist as per your availability as a fab lab. Okay, as a designer, you are just thinking about the circuit. As a designer, you are just thinking about the circuit. Okay, we want this type of gain and we want that just like this. So you talk about the circuit design. But if you know about the layout, you can understand the problem of the analog layout designer. And if you are aware about the analog layout, you will replace this resistor with a MOSFET there. Is it okay? That is okay. You can increase the gain by the help of cascading of that MOSFET. You can increase the resistance. And let's check what is the resistor, what is the gain here. We will discuss what will be the gain. The swing is not that much. The swing is not VDD, it is VDD minus VD sat. But the gain, let's check about the gain here. Okay. So you have a MOSFET, you have an input, you have a here, and you have a V bias here, and you have a VDD, and I am using like this. And you are talking about the output at here. You know what is the small signal model of this model. I am just designing this model because we know that we discussed this, what is the small signal model of this. And if you want, we can design that. You have an input, you have a this, and this is GMVGS, and you have a R01. Let this is M1. So this is R01, that is GM1, RVGS1, and GM1 is the large signal parameter that will be set by the operating point. That will be set by the operating point. And the gate voltage is make it V in plus delta V. So this is delta V. Okay. So that this is like this. And the source is grounded. And you are talking about the output at here. Now I am talking about that PMOS as a load. So simply you are talking about what, that you have a current at here and this is connected in such a way like this, and this is R02. This is your source. Now the source is VDD. In a PMOS, source is VDD. So in a small signal model, it is act like a short circuit here. And this is GM2 VSG. Okay. And if you talk about what is the gate voltage as V bias is what? If you are talking about the gate voltage here, what is the gate voltage with respect of this? This is grounded there. Why? Because V bias is DC voltage and it is grounded. So what is VSG? The source is grounded, gate is grounded, VSG is 0, the GM VSG is open. So you can replace this MOSFET with a R02 only. The small signal model of that circuit is like this. This is R02 with the small signal model of like this, delta V. That is very, very simple here. Just replacing here that, okay, this MOSFET small signal model is R02 only. Why? Because the gate voltage is fixed, the source voltage is fixed, the VSG is fixed. So source and gate is grounded, 0. So VSG is grounded. So basically that you have a GM VSG is open. And if GM VSG is open, that is the only resistance R02 is present there. Okay. And what will be that V out by V in, yeah, V out by delta V is what? That is minus of GM1. That we discussed that it is always minus of GM1. Why? Because this is GM1 into delta V. Because source is grounded and gate have a delta V. So this is GM1. This is R01 at V out with respect of ground. This is R02 with respect of. Basically, R01 and R02 are in parallel. If you are looking in such a way, okay, this is a node V out to ground, it is R01, V out to ground is R02. So R01 parallel of R02. So that gain is minus GM1 R01 parallel of R02. Yes. The gain is minus GM1 R01 parallel of R02. In a diode connected, that was minus GM1 upon GM2. Okay. In a current source load, you are using a MOSFET as a current source load. That current is that gain is minus GM1 R01 parallel of R02. The gain is higher there. In a resistance load, minus GM RD parallel of R0. So if R0 is very high, it is minus GM RD. If RD is very high, that is minus R0. Minus GM R0, that was intrinsic gain. But if you are using a high resistance, that will be a problem in terms of layout. So you can replace your resistance with a current source load with a PMOS or NMOS. If you are using this circuit, so you are reducing the area. As a layout designer, as a circuit designer, you are not have a resistance. Of course, if you don't have a resistance, it is not have a heat. Resistance always absorb the energy in the terms of heat. It is dissipate the energy. Capacitor store the energy. Inductor store the energy. Capacitor store the energy in the form of electric field. Inductor store the energy in the form of magnetic field. Capacitor resistance dissipate the energy in the power, the heat. So if you have a resistance, resistance will be heat up if the current is higher. That power is equal to I square into R, या V square by R. And if you are using a MOSFET, the MOSFET is perfectly work here. Okay. So that's why whenever you are talking about, always we are using a PMOS as a load. Why? This will be help you to provide a higher resistance, higher output resistance there. Just make it in a saturation only. Just make that MOSFET in a saturation, and if you have a in saturation, that this MOSFET will provide like this, and the gain is minus GM1 R01 parallel of R02. That gain is very high there. Is it okay? What is the limitation of that? The limitation is not swinging from VDD to VD side, it is swinging from VDD minus VD side to VDS of the NMOS, and VDD minus VD side is PMOS. Okay, that is the one only limitation. But the gain is very, very high. That is minus GM1 R01 parallel of R02. R01 R02 is very high if you are using a MOSFET in a saturation region there. If you are using a MOSFET in a saturation region, R0 is very high. Okay. Ideally, it was if you are using like both resistances same R01 and R02 is same, it is minus GM1 R01 upon 2. If this is high and high, then let this is both are 50 kilo ohm and 50 kilo ohm. So that is minus GM1 25 kilo ohm. Is it okay? So you can use this type of stage also. Okay. Okay. Yes. Anyone have a question? Sir, why common source amplifier with resistor we called is source generation? We discussed that. Okay. Yes, register. Yes, dear. Register is very bulky in layout. Yes, dear. So, okay. So this is the way you can understand. Let's talk about that last circuit you have. I am not going for the source degeneration. I am going for again of CMOS inverter. That is also called a amplifier, that is common source amplifier, that is called active load. The load is active and I am using a PMOS here, and the gate is common as a V input. We know that common source, that is an inverter, CMOS inverter. It is the CMOS inverter. But when you are talking about the as an analog circuit design, this is a common source amplifier with active load. This is a circuit of common source amplifier with active load. If you talk about the digital, this is an inverter only. Okay. So what is the beauty of that circuit? Just think in such a way. Okay, you have a ID versus V out. So if you are looking this circuit, that what is that VGS is V input here, and due to this you will find that current is like this or like this as per the circuit you have. But in PMOS, if you are thinking that this is VSG, okay, it will provide that the current in the third coordinate, but I am just shifting in such a way to make that both MOSFET in saturation. If both are in saturation, I am just shuffling that current. That current is like this. Yes, everyone. So with the resistive load, if you are using a resistive load, so by the resistive load, that you have a DC operating point as a straight line with a negative slope. If you are using as a diode connected base load, that is 1 by GM1, yeah, 1 by GM2. If you are using a PMOS, it is also provide that, but it is not dependent on the input. Here the input is same for both. And VGS for NMOS, that is V input minus 0, and that VSG is VDD minus Vin. So basically they are perfectly matched. That for PMOS it is VDD minus V input as a VSG, and that for NMOS it is Vin minus 0. It is basically working perfectly. That for input the graph is like this, and for PMOS it is the graph like this. And if you are talking about the saturation region, that are perfectly saturate here, there, that have a wide area of saturation. If you are using a resistive load, that have a limitation of the saturation region, that resistance will defect your saturation. It will be going into the linear region. If you are going for higher RD, it will be greater from VDD by RD is the current. If you are increases the resistance, that VDD by RD1. Okay, so that the operating point is the DC load line is not that much good to make that MOSFET in saturation region. But if you are using this type of circuit where the PMOS and NMOS have a same gate voltage, in with respect of ground, this is VGS is V input. With respect of V in, that VSG is VDD minus V in, that is both have a same voltage at the gate side. And both MOSFET is perfectly defining in such a way. If you are going for the characteristics of the PMOS and NMOS, so that PMOS and NMOS both are in good in saturation, that is provide a high, that wide range of saturation. And let this is M1 and this is M2, just determine it. Okay, just you make a small signal model and determine it. This is your assignment also. What is the gain? That will be, let this is GM1 plus GM2. Of course, this will be a minus of GM1 parallel of G plus GM2 R01 parallel of R02. Just check it. Just determine it, that what will be the gain. The gain is AV is equal to minus of GM1 plus GM2, both have a current, will be that transconductance will be added. And this is one of that question that IIT as for MTech or for an interview for a TI for ST, they ask in such a way, okay, tell me what will be that total transconductance of that, what is the overall gain of this circuit as a common source amplifier. This is a common source amplifier as a resistive load, not sorry, as an active load. Okay, if you are talking about as a inverter, that output is like this, V out is in like this. So I am not talking about this region, I am talking about that region where the MOSFET in saturation, this region. If you are changing that some voltage, it is the output is changing at very small change at the input and large amount of change at the output, and this will provide a that much amount of gain. Okay, so I am talking about when the both MOSFET in saturation there. Okay, and how that make is saturation, that PMOS as a load and NMOS is active, that PMOS as active load and you have NMOS is a behave like active circuit, so it will provide a good region of saturation. And if you have a wide range of saturation, it will provide a high range. That swing is that for a small change you will find a large amount of change. Okay, so you can. Okay, so this is the assignment for you. Please work on it. What will be the make the small signal model and justify it. Okay, what will be the gain of the that is an inverter. Okay, or common source amplifier with a active load. In our next class, we will discuss source degeneration, common drain, okay, and what will be the common gate. So firstly, we will discuss source degeneration, then we will discuss about the common drain. Okay. Okay, if the time permit, we will work on one project as a common source amplifier have a gain of 20 dB or 30 dB. As per that, as per the what is the requirement of the design specification, on the basis of that, we can design one project also. Okay. So for now, thank you so much, everyone. Please we work on that and complete this assignment. We will join on next Saturday. Thank you so much, dear.